Hello. My name's James, and we're going to do the first of a series of demos today. So this is going to have a little bit of a different format from the tutorials. And so basically what I'm going to do is kind of go through the why am I doing the things the way that I do for in-situ matchups. And then I'll briefly kind of just go over the code. But the whole point is to just throw all this code at you so you can copy paste to your heart's content. So try to make things as easy as possible. I did sort of organize all my scripts so that hopefully you can just steal what you need, whatever you need for it. So first up, this is the in-situ matchup demo. I have maybe 6 or 7 slides just kind of going over what is a matchup, how do we classify like the quality control needed to make a good, nice validation matchup between pace and field data. And then for the spicier people that like to do radiometry, remote sensing reflectances, I have a little bit of a commentary on what you have to do as extra bits of information compared to the people that do like AOT or chlorophyll concentrations or something like that. I have some thoughts on some transects, if you are one of those that just goes on a ship and goes for a very long line, the different kind of thinking that you have to do for matchups, and then I'll just kind of showcase how I do some of the statistics for the pace validation website, if you've seen that page. Super fun one. So first up, what is a matchup? What is a matchup? Try number 3. So the way that we do matchups, I have a AAOT site off the coast of Venice over here with a star on it. We have this nice little flowchart called the Bailey and Wardell matchup criteria. And the way that works is we have this nice station of data, and I want to see what makes this work for a satellite matchup. So first, what we do is we take a 5x5 box around this station in terms of like OCI pixels or whatever your satellite is of choice. And so we take this 5x5 box and then we look at the L2 flags. And so in our OCSSW software, we have a series of quality control checks to let us know whether there's like high glint, or maybe the sensor is at a weird zenith angle, maybe the sun is at a weird zenith angle. So let's just toss all those things immediately, or maybe a cloud flew over in that 1 pixel or something like that. And then whatever we have left over, we basically do, let's toss anything with bad geometry. Let's take the standard deviation of it. Let's keep everything within 1.5 standard deviations of it. Let's do some checks on the signal to noise ratio, make sure that everything's not super wobbly. And then whatever we have left over, we just take the average of and then report that as our validation spectra for OCI or FEARS or whatever satellite that you're doing. And so this is basically it. So whenever you're running stations along your transect or anything like that, or you're pulling AirNet OC data or something like that, this is what we do to call a validation pixel. It's just a 5x5 box, get rid of some bad pixels, do some stats on it and make sure we got good data, and then run it. And now we have that average spectra. Good so far? I know I just threw everything at you. Okay. So what is this actually from the bottom up? So at my station, I have this nice little CML sensor, and it's taking all these really awesome sky and water leaving radiances and giving me all kinds of really cool radiometry that I can start using for my data. Well, I have to do some corrections first. First, I have to remove the atmosphere, and what we do is we basically have to run our transmissions through the atmosphere. There's a lot of atmospheric correction that we pull from ancillary data or from the station itself. Then we see that this sensor is looking at an angle to the water. Well, let's model it as if it's looking straight up and down. And then the sun has to be completely directly overhead, and the water is directly below in your instrument. So that's how we model it. This is called the BRDF correction. And I have sort of some stats in there that there is codes that you can just use. The OR Morel is our bread and butter for that. We just use the Morel 2002 BRDF correction for that. And then, well, we have all this water, and it's got variability in it. Well, let's smooth that out. That's all we do. We basically take the wind speed and do what we call the R-Gothic correction, and that basically lets us model the ocean as a nice flat surface at a perfectly atmosphere removed, and our station has no fun geometry associated with it. Oh, it's not me. Haha. And then now we have really good matchup criteria. This is what the satellite sees. So now we've turned all this like fun, fancy, atmospheric influenced data and made it to where we are just looking at what the satellite should be seeing in that case. So good on that. This is how we do radiometry. So this is the whole point of this is to say that when you have field data, you have to make sure you're doing an apples to apples comparison between what your field site is seeing and what the satellite is seeing. So if you're doing radiometry, that means you have to do some corrections first. Correct for the atmosphere, correct for variability in the ground. If you're doing chlorophyll, cool, you don't have to do this. Great, move on. So good for that. Yes?
Why do you go straight up and down when the satellite is at an angle it's tilted? It's not straight up and down.
Correct. The satellite, remote sensing reflectance, when you model, when we at ODPS process the OCI data for you, it is remote sensing reflectance which is modeled straight up and down. So it's already been BRDF corrected so that you can do this kind of thing, because it gets really spicy when you have angular measurements and you're looking into the glint or not, and then now your field data is all messy. So it's a good question. Also, feel free to interrupt me throughout. So I have too much coffee and I'm just bouncing around right now. So transect thoughts. I've been showing you the station data. There's a lot of really cool teams that are going out and making really awesome measurements, sometimes going out for a month at a time, longer, and taking really cool biogeochemistry, Dalek data, remote sensing reflectances, and they get really good points. Like a lot of work went into taking these 8 measurements. Like this is probably a day's worth of filtering, extraction, moving through and getting a chlorophyll concentration for it, depending on what type of chlorophyll measurement you're making, if you're doing like HPLC or fluorometry or maybe everything. Well, that's great. If I plot this on a plot with lat long, it looks really cool. I have, like if I'm starting off, where's my mouse? If I'm, moving a ship through, I have really low chlorophyll values, and then I turn and, oh, I might be in a little eddy over here. Wow, I got some really decently high values, and then I left it again, and then I move up. What happens when we actually look at what the satellite is seeing? We have these really weird things called clouds. And so we have all these measurements, and we worked really hard for them. Well, PACE is giving us really good data. It's hyperspectral. We have all these really cool heritage products, and we can plot the chlorophyll concentration on it. Well, that also means that my validation points, they're not very useful under these clouds. I can't really use them as validation. So that's why that whole process for taking a 5x5 box, taking the flags out so that I don't have cloud contamination or something like that. And then really, when we're doing validation, we have so much really awesome data. Like when I plotted maybe 3,000 or 4,000 matchup criteria points. And when I look at them just as is, they gave me really good QUIP scores, which is Ryan's AVW check that lets us know how quality our remote sensing reflectance spectra are. Well, they're really good, but I still can only use maybe 10 or 15% of the data. So don't be alarmed when you're doing your own field data matchups and you realize, well, I don't really have that many. Well, this is why. Good so far? So what happens when I do have these nice 10% to 15% remaining points that I want to do matchups with? Well, I can start showcasing the statistics of how well my 2 observations are actually corresponding to each other. So we all know and love the plot on the right. This is a little scatter plot where we plot one variable against the other, or one instrument against the other. And we have a nice little spread. We can calculate the linear regression statistics, maybe do some type 2 regressions if we're being fancy. But there's a lot of stuff that's kind of hiding in these types of plots. And so I'm going to channel my inner Kirk here and, and showcase the Bland-Altman plots, also known as the Tukey mean difference plots. And so this is basically what we pull from like biology, medical experiments where they kind of showcase different drug matchups and things like that. I don't know the whole story behind that. Kirk has a really nice read-up on that on his repo that I stole this from. Thanks, Kirk. And so what we're actually showing here is we take the mean of the 2 values and we just plot them against their bias. And so this doesn't let anything really hide. And so now we have like, okay, I have variability in one of my measurements. I'm going to take them and see, okay, does my other instrument give me the same variability, or am I within that type of variability? And so when I have that, I can actually go across low values for each to high values of each and show, hey, my bias is doing pretty good. I'm within the variability of it. And I'm not biased when I have high values or low values, like specifically. There's no systemic thing. And so what I did here was I took all of our PACE OCI and ARNet OC gold standard matchups, and I kind of just took out anything that was above 0.4 milligrams per cubic meter of chlorophyll concentrations, or at least measured derived chlorophyll concentrations. These are blue waters. That's great. Now we can show that we're really, really doing so great stuff. The bias is not that bad at all, really. It's very, very small, 10 to the minus 5. I'll talk louder. But when I do the ARNet OC all sites matchups, I start seeing, okay, my plots have kind of changed up. I don't have that nice little limit of agreement area where my variability in my field is being like constrained at low or high values. So what this means right here is now I know that, okay, when I have higher remote sensing reflectance at 443, I might have a slight positive bias that's scale dependent. And I show that OCI is showing us higher values when we do field and satellite high measurements of remote sensing reflectance. Or maybe at the super low values, I'm biased negative. So now I have this sort of scale-dependent bias that lets me know, hey, there's some really fun things that we can start exploring in the algorithms. This is kind of a hiccup or something. This is letting us know there's more work to be done. Maybe we need to make algorithms better. Maybe we need to kind of like showcase what regions we're looking in. Maybe our algorithm's just not built for this type of data. So there's all kinds of really cool things that you can start highlighting out. But in the scatter plot, you can't really tell. It's kind of like, yes, there's a linear regression, but maybe it's not really showcasing that it's significantly different from that 1-to-1 line. So this Bland-Altman plot's really, really handy if you want to kind of like dive into the statistics in a different way and sort of like highlight some of these things that we can sometimes brush under the rug, especially if we put everything in a log-log plot on the scatter plot. That's my favorite way to hide everything that's bad. So I want to leave on this part because our field validation teams for the PACE validation science teams, there's 30 teams-ish that are going out and taking all this really, really awesome hyperspectral measurements. And so this is why I was complaining that, oh, well, how do I actually make this a dynamic plot? So that's why I threw my project out for everybody. So yay! I do have a team working on this, but I like showcasing this because it's a nice little GIF of just showing what these Bland-Altman plots look spectrally. And so we do it every 5 nanometers, the entire spectrum, remote sensing reflectance. You can see how sometimes in the UV we don't have really good matchups at all. We only have like 33 points in the UV. So if you're looking into making more measurements in the field, try to aim for that UV. You'll be contributing to a lot. So on that note, I will transition awkwardly to my in-situ matchups data notebook. So once you pull and load up the satellite in-situ matchups 2025 from the website, you can download this. And you can get kind of a summary of like, here's what ARNet OC is. In this tutorial, we're going through, and you can read through and kind of go through the learning objectives. We also did this last year. There's a video of it and some slides if you wanted to go through that as well. But what I did was I shoved every one of my functions into this thing right here. So I set up all my constants, and then I organized everything by general utilities. I tried to doc style everything as much as I could so that hopefully it's just plug and play, copy and paste, whatever you need it for. The next section, we're going over the ARNet OC utilities that I did. So this is how I pulled the ARNet data and then organized it and put it in a nice little pandas data frame so that we can actually do some work with it. And then I kind of show the satellite utilities. Here's what I did to take OCI data. Here's what I did to find the quality control flags, to organize them, to take them out so that I don't have to run them in my statistics. And then finally, I have the matchup, second to last, I have the matchup utilities. So this is where we do that Bailey and Wardell criteria that I show you. So I take my satellite data, my field data, I say, what's my signal to noise ratio that I need? What's my sensor zenith? I can change this. Maybe I want to see if I have really decent matchups at high zenith angles. Maybe I was in the Arctic trying to measure things, and I don't want to throw all my stuff out just because, well, there's somebody telling me that I shouldn't do it. Well, you probably shouldn't, but you can try it anyway. And then after that, I did put the plotting utility. So you can actually just pull this plot BA versus scat code, and it'll run all these things and do all your metrics for you. And you can kind of see how those statistics come together. I have little dictionary outputs if you want to really pull out the stats and start working with them. And just kind of like my James style of just shoving plots together. If it looks good, I stole it from Kirk. If it looks bad, it's because I altered it myself. So that's the way I'm going to say that right now. And now that we have all that code out of the way, I can kind of briefly go through. We'll go back to the top. And I just kind of show, here's how I use my process AirNet function. And then moving on to the pace OCI granules, I have my lat longs from the AirNet data. I'm going to pull my satellite data. Get sat TS matchups, time series matchups. I have a start, end date, my lat long, and this is what I do to basically access Earth access in my style because I'm lazy and don't want to have to deal with all the bounding box stuff. I just do time points. But because this takes a very long time to get decent matchups, we had start date of, I'm just going to assume March 1st for OCI of 2024 and then end it like June or something like that. It takes a while to pull all of those points. Like Earth Access does a lot of the work for you, and then Xarray has to can let you lazy load. But once you actually have to index into your lat long values, you have to load the data. So to do that, you have to go through all this data. So I'm just going to speed through it and give you pre-cooked data. So yes, Eli.
Question, if you could go back up here.
Yes.
So your lat long is just a single value because you have the hard coded in the 0, the first one. But does your function take a vector of like lots of different lats and longs?
It could. So I have notes in there for people that want to start converting this into transx, which would be a series of lat long coordinates on how to start going through that. The issue for that is when we do the satellite pulls, I do the 5x5 box extracts in there for you, and it gets kind of broken when you try to give it more than 1 point. So this is, that's a really good question because this basically lets you know that this is built for station data. So I have a time range of a station, 1 coordinate at a time. And so if you want, you can break into it and make it go over a bunch of different points, or you can just loop through a bunch of different stations with different time ranges. So great question there. Yeah. Next up, this is where I say that I was cooking the turkey in the oven for a while, and we already have one pre-made for us. So I pulled this data. Insider knowledge, we have version 3.1 coming out, but it's not out yet. This technically is the version 3.1 data for AAOT. So if you want to use hot off the press where the press isn't even there yet, use this data. But it's only 125 points. Good luck. And then here's what I do for the matchup criteria. If you have a question on how a function works and I'm not around because I'm distracted easily, you can just do question mark and then your function. And it prints out that nice little doc string of like, here's my input parameters. This is what I want to do. And then, hey, heads up, there's a note here that says maybe this doesn't work because this is for stations only. And if you have a transect, you're going to have to do something else. And then you run it, and then it makes a nice little data frame in Pandas for you. Outputs this nice big giant matchup, 125 matchups for you. And then you could just, pull out the wavelengths and make plots with them. And so this is just basically showing you my thought process on how I pull out field data, satellite data, match them up, make some plots. That's pretty much all this is. So heads up, the demos are all pretty much like this. We just kind of throw code at you, and hopefully it's useful. And if you have other things that you have questions on, let us know. And so here I'm just plotting, Modus heritage wavelengths. You can kind of see, hey, AAOT, it's doing some really nice matchups. I can plot other variables, and I see, oh, 667. There might be a little bit of a bias dependency in there. So nothing can hide from these stats. So with that, I will leave for questions before we transition to Riley, who's going to go over even fancier ways to do time series data matchups and stuff and different period things. I'm not going to ruin it. No surprises. Dun, 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 dun. I did the fire hose thing, didn't I?
James, when you said we could use your pre-cooked data, can you say again where that data is?
Oh, yes, sorry. When we pull that out, I dropped it in the shared public database, the directory that has all the shared data in there. There's Pace Hack Week. It's also hard-coded in as an absolute link in the function, so you can get the absolute location of it in the thing. But it's in the shared data Pace Hack Week folder.
And James, just to add a comment, so the reason some of these plots look like this one right here, and without the green shaded area, if you go down to the green one with the green shaded area, maybe down.
It's over here.
Right. So what's happening in that code is it's doing a statistical test on scale dependence in the bias. It's seeing if it's a flat line or not. And the reason the green shaded area, that's the so-called limits of agreement, most of the data are within that range. It only makes sense if there is not a scale dependence bias. So it only plots this if it's a flat line. So that's why some figures look one way and some look another way.
Yeah. And then something like this would be like, oh, if I have high values, then I might be more positively biased versus low values, I'm negatively biased. Bing wong.
I
Ready.
actually have a
Hard
question
questions.
for both Kirk and you. For this situation, what's the take of that? What should we do about it?
There might not be anything you can do. It just means that mean bias doesn't mean anything because it depends what your parameter value is. Does that make sense? So it's almost like a negative result. It just says that the numbers here, the mean bias and limits of agreement, they don't make sense because there's a scale-dependent bias. If you really want to play with the data, you can start doing things like screening out data. So, there was a case I was working with once where it was actually a physical machine that we were comparing. Above some threshold, there was a scale-dependent bias. Below a threshold, there wasn't. So if you split the data that way, we knew like, okay, it agrees within this range when the values are, between 0 and 5 or whatever it was.
And other analyses, before Anir, go for it. He might have.
Each of
he's
these
gonna say
data
what I was gonna
points
say.
are supposed to have uncertainty estimate on it from the satellite products and the in-situ data products, and that will definitely have an impact on how you do the matchups and the linear fit and the statistics. So that's one thing that our team is working on, is to add the uncertainties from these products and then redo the
Right now,
analysis.
this assumes that there is no uncertainty. So whenever I do the standard deviation of the variance,
Like,
it's 1.
yeah. Some of these outliers might have really large uncertainties in them, so it'll have different impact on the fit.
Sorry, the mic is important just so we get it.
Dun, 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 dun.
Yeah, I'm sorry to, so also in this code base, there's a way where you can normalize the bias by the squared uncertainty. And so that's useful because sometimes your uncertainty varies, in different situations. So doing it that way, you make sure that you're testing, do things agree within stated uncertainties?
Yeah, that's I make sure that normalization is basically 1. So there is no uncertainty in it, and your stats will showcase that. So there are ways, if you know your uncertainty in the field data, just plop those in, and it will do a better metric.
Sorry, I have one more question. This might not be obvious for all of you because Amir is here. So, so some of the wavelengths works really well, some of them not as good. So I wonder, do we understand why some of the wavelengths works well, and some of not? Naively, I would think the blue wavelengths will be working worse than the longer ones, but it's not obvious. It's so they by looking at this result, it's not that simple. Seems to me.
Yeah.
I wonder, what do you folks think of that?
AirNet specifically is AirNet OC. Most of the sites that we're using for our validation are located in pretty decently coastal regions. The water is quite variable in there. And so we're going to have really good L2 corrections, which Amir is going to say.
Yeah, no, I was going
Thanks,
to say.
Amir.
I blame James for this. No, okay. This is,
like throwing
I
everybody
believe this
under
is AAOT, right? So
Yes, this is AAOT.
It's one site out of dozens of sites for Internet OC. So this is just one sample. So I would definitely look at broader statistics than just one site. This specific site is pretty coastal. If you look at the matchups, you definitely see different performances at different sites. So you'd have to play with this and look at the overall matchups of different sites. But it's definitely more challenging to do coastal atmospheric correction for sure. And this is something that like polarimeters and stuff like that can definitely help with.
And I think when we throw all of our AirNet OC sites, this number increases. I just picked the one that had the most matchups, which is AAOT. If we put everything together, I think we have about 600 matchups now. So this is a pretty decent chunk of those.
Sorry, Amir, I have another question for you. We can also talk about this later. But for the atmospheric correction for version 3.1, are we expecting a better agreement in the blue wavelengths?
This is 3.1, right?
Yep.
Yeah. So this is 3.1, and I think overall the agreement did improve at 3.1 relative to the version screen right now, version 3. We haven't looked at specific sites. This is actually the first time we do this specific, like one site at a time. The data is typically published as all of the sites together.
Yeah.
What we call the golden sites. So this is some of the sites
Yeah.
that and basically put the plots for all the sites together. At the same time, this matchup seems to be.
Yeah, but hopefully it's going to be like addressing the like past 480 issue in the blue, yeah? Or making it a little bit better?
That one might still be in there, right?
Sorry, I can also ask
Which
later.
wavelength
but
range?
sorry. Anything, at least for like my water, anything past 480 starts to, no, like, sorry, very, very blue. So 480, like, up into 500, and, like, that's fine. But the blue is, like, I'll show you plots. I'll talk to you later. But sorry, thank you.
Yeah, well, that's our bluest one that I show here, and yeah, things to work on. Yay!
Thank you, James.